they are trying to buy our radar and that do forecast landslides and say, remember that we started with a very simple instrument that is a tele distance measuring by a laser. So what is the advantage of the laser? You want to have a very, very high energy beam and the beam very narrow. Because if I want to measure in the 3D now the distance between my position and these glasses, I want a beam as narrow that goes only to these glasses and goes backwards. This is a sense of the tele-laser. Okay? So I want to create what it is a very narrow beam and very high energy. Because if my beam is as narrow as 1 millimeter, I can have a reconstruction of all this environment with a resolution of 1 millimeter. Every place in this space, not in the 2D, in the 3D space. So think how many cube meter are there, and think how many cubes of 1 millimeter by 1 millimeter you have. You say a billion of small cubes. In fact, it is possible only in this time because there are the software that are able to handle large cloud of small pixels. Large means tera cloud of pixels. And to have a narrow beam, you must generate it to have 1 millimeter at a very long distance. This is not a black body. Okay. So we started with a black body. It's a very big source of energy. Unfortunately, it has a great drawback. The energy goes everywhere. So you cannot have a lot of energy only in one point. A black body, a lamp illuminates everywhere. I cannot measure a distance if I have a beam that is as wide as an entire wall. I want a very small and very energetic. Very small because I want to look at only one detail of 1 millimeter, and very energetic because I do the distance on remote. Maybe I am on the satellite. So this year in September, in August, for the first time, a laser on a satellite has been launched from Guyana, and this is a very new mission, and his name is Eolus. That is the Greek name of the divinity for the wind. So he is using to measure the wind by using the laser, because it has a laser points to the atmosphere. In the atmosphere there are particles, the particle moves. The particles are millimetric particles. The particle reflect, you get it. And this was, and Aeolus, the laser was made by a big Italian company that is named Selex, and it is the first time that the Selex, they studied for research for a year how to make a laser working in the space, and now we have a laser working in the space. This will be a LiDAR. And the radar is not really different from the laser. Apart from the fact that here we work with micrometer and here we work with millimeter wavelength, so the resolution will change because change the scale, but of course a radar has a very wider beam than a laser. So this is a laser. A laser is, let us say, 1,000 times because it has 1,000 times the wavelength, but is propagating to the cloud, to the forest, to the snow, and so on. So what is the chess? Of course, what is the problem of the black body? The black body is actually an isotropic emitter. Isotropic emitter, it means that if you have this power, the total power of the black body, and the energy goes everywhere in the sphere, if you have in a position that is a distance r from the black body, the density, that is power divided by surface, is just as the total power divided by, well, what is the surface? The surface is 4 pi r squared. Okay. So the density is inversely proportional to the square of the distance, and every telecommunication guy knows this because this is also the amount of energy that you get when you are at the distance from a base station. So the energy goes with this strong attenuator. However, if you are directional, 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 okay, that is different because it means that you can concentrate your energy in a very small angle, okay? So in a very small sector of the space, and I can say that how can I get the energy, the density? The energy is all the power of your directional emission divided by what? Well, the power divided by this surface, okay? Of course, the density is always a power. It means that here the power goes on a pi r square surface. Here, the P, the power, goes on a smaller surface. And if the surface is very, very small, this number becomes very big. So you don't need a lot of power, you don't need the sun to have a lot of energy, because you can make the surface to be very small. We will see that a laser is much powerful than the sun by the fact that the point here is small, even if here is much smaller than the sun, you cannot emit all the power. So basically, you can relate, you remember that we were putting the definition of solid angle. You remember the solid angle is just the surface divided by the square of the radius. It is the surface divided by r square, okay? So instead of writing in this way, we can write in terms of solid angle that is r square multiplied by omega. Okay? Let us say the density of a black body and the density of a directional. And so you immediately find that the density of the black body, or the density of a directional source, related to the directional density of the black body, okay? Well, even consider that you have, of course, this term that is the power that you create related to the power of the black body, but you have another term here that is this that goes as the numerator for pi, because r square actually simplified, divided by omega and r square simplified. Okay? So you have a directional gain that is this. This is GD, gain due to directional. Because you are very good to concentrate all the energy in a small angular fraction, in a small solid angle in the world. Okay? This is a trick of an antenna. Okay? Every one of you who works with antenna knows that antennas are qualified by what it is called a directional gain. So the antenna say how much better is with respect of an isotropic emitter to concentrate the energy only in one direction. But this is not really a property of antenna, it's a property of any electromagnetic wave. So it works also in the optic. Also, let us say, our cornea, also our lens, also our glasses, everything behaves like an antenna. And when we speak with this, we speak of coherent sources. Coherent is the term that is used in optics and also in radar now to say that we have a sort of synchronization. And this is the topic of our lesson. So how we can get synchronization, because this is very important. We want to get access to the very high directional. So if we wanted to have a very strong sources, it's like you put some, let us say, people. I'm not as good as other colleague of mine to make a drawing, but you have a lot of young people at the edge of the pool, and here you have the water, and all these people have, let us say, they have a foot on the water and can stamp a foot on the water. So when you just plug a foot on the water, you generate a wave that is, let us say, a surface wave. And of course, many of them has exactly the same foot on the water, and you want to use all of them to generate a very strong waveform, for example, moving in this direction. Okay? How you can generate it? You must synchronize all this guy. Because if anyone taps the water by its own, for example, one taps the water with this frequency and so generate wave with some wavelength, and one taps the water with this frequency, and one taps the water with another frequency, and you sum at some position, you see that here you have a maximum, a minimum, a zero, so the summation is a small number. Okay? So if anyone has a different frequency, it does not work. So it's like when you do step or when you do your gym, that you must synchronize. So there is someone that gives you the time, and every people plug exactly the foot in the water exactly the same time. And if you are very good exactly the same time, you have the same frequency. The same frequency is better, because if you have the same frequency, you have an opportunity that the wavefront put together. Of course, I want this. So this guy generates his waveforms, this guy generates his waveforms, this guy generates his waveforms, and when, let us say, for example, you go in this direction, you see a big wave that is coming, because here you have the coherent superposition of the effect. Okay? Coherent superposition of the effect. Incoherent where they are not synchronized. Coherent where they are synchronized. And for all, it's not enough to have the same frequency, but you should have the same frequency. The same number of taps per second. Okay? This should be the same. In fact, you have a clock, you have the music, and the people dance or move, or in fact, you perceive dance that is something that is good. It's not a disorder as many people work. Let us understand better how it works in the 1D, okay? This is a two-dimensional case. Then, of course, here we speak of the 3D world, but maybe in the 1D you understand better. Because if you have one source that is generating one sinusoid, and you have one other source that is generating another sinusoid at a different frequency, and another source that is still at a different frequency, and you sum in any position, you don't have a big number. Okay? Because you have here, you have a minus, here you have a zero, here you have a plus, and you have some, let us say, average of this summation. We can put mathematics, it's not complicated. But let us first think that, okay, if the frequency is different, no way. But if we have the same frequency, it's not enough. Because if one is generating this wave, and the other guy is generating this wave, so this one, when one plunger is foot, the other is up, and when the other is up, the other is down, then you generate two waves that are exactly opposite. And once they sum in any position, the result is zero. So, first of all, it's enough to have the same frequency. And the same frequency, it means that it should be a monochromatic source, one color. Okay? So for the light, it does not appear so. But for the laser, yes, the laser is always one color, and the radar is one color. You can be almost monochromatic. I think you can have small frequency with respect to this, so you can have a bandwidth, but very small. So first of all, it should be monochromatic. Okay? If it is not monochromatic, it's a nightmare to synchronize. Second, the phase should be the same. Because if you, now you state with a phase 0, and here you state with a phase 100 degree, you get nothing. So phase is the same. So to get coherence, you must have same frequency, but it's not enough. You must synchronize also the phase. So if you have many sources that are coherent and synchronize the phase, then you get the gain. Okay? If you want to understand how it works, here we can count the number of wavelengths, okay? But we can, instead of expressing the wavelength, you can express the phase. The phase, it's a number, it's a complex number, okay? We can use complex number. I can assume, for example, that each one is generating a sinusoid. So let us speak of a vector that is rotating in the space at some frequency, okay? This is another vector that is rotating at the same frequency. So this is, for example, the frequency of rotation is 1 cycle per second, and also this is rotating at 1 cycle per second. Okay, so 1 Hertz and 1 Hertz. If they are rotating together and you sum it, you don't have a good number if they have a different phase. But if you have the same phase, now the sum goes very high. And just to make some simple case, to understand how much you gain, for example, by the coherent and the non-coherent case, let us consider that you have same frequency, so only the phase changes. So you can have, in the d-dimensional case, you have n sources. But now we consider the case of random phases. Random phases, it means that one source has this phase. They have all the amplitude same, so the amplitude is always 1. Okay? I have one source with this phase, one other source starts with a different phase. Okay? Here I consider only 2, but let's assume a large number of sources. Each one has a different phase. Okay? And then we want to put all together with the source. We sum this vector with the rule of the parallelogram. You know how to sum a vector, okay? Do you know how to sum vector? If I want to sum this and this, what I do? I just took this and I took this, and the summation is this vector, okay? But if now one vector goes there, and another vector goes down, and maybe a vector goes here, and the vector goes here, in the end the summation does not go much far from the origin. Okay? This process is very famous, it's called Brownian process, is a drunk man process. It's like exactly a walk of a people, of a drunk man, that every time he randomly moves his step. So he's looking in this direction, then he moves in another direction, then he moves in another direction. So the direction change is random. And he is always to the same step. And this is a small step, it is old, like me, or it is young, it's a big step, but does not change too much, because in the end, you are not far from the center, okay? And if you wanted to make it into equation, well, that's not too complicated, because I can say that the total summation of random phases, of n random phases, you just put this, okay? Simple. Is just summing the parallelogram. I can say that if the phases are, this vector are many, it's like a cat game of the rope. When you have a rope that is, everyone try to move the rope in different direction. What happens to the rope? Does not move at all. This is random. Random means non-coherent. Actually, it moves a little. If we wanted to know how it moves, we have to understand what happens of this. So phi is a random variable. Random variable, phi minus pi and 2 pi. So it can be any direction in the circle. And if I want to compute the average position at the end, so the average of the summation, what do you get? Well, by mathematics it says that the average of a sum is the sum of the average. Okay? And phi is uniformly distributed from minus pi to pi. So it means that basically to average you must you can think that phi has all this number and the average is exactly 0. Or if you want, you can compute mathematically this number. But here again, if you do the expectation of a variable that is of the cosinus of the cosinus of the variable take all the number between -1 and +1 and you do this expectation. So you average the positive, let us say the positive and the negative compensate and you get exactly 0. So whatever you do your evaluation, this number is 0. So what it means is that when you sum independent number, what you have as a summation, you remember, in statistics, when you sum independently distributed variable, Gaussian. So x is normal distributed. Actually, it's a normal circular, it's bidimensional because this is a complex value as a real and imaginary part. It means that if you look at x, you see that it's a Gaussian in this direction and also a Gaussian in the other direction. So it's like tail. If you look at x as a function of the real and imaginary part, a bidimensional Gaussian is like tail, okay? That goes very rapidly to 0. Okay. And the higher probability is 0. So this means that the Gaussian is also centered on this. So the average, it means that if you want to find your Drunkman, you will look at the origin, because here it's a higher probability. But of course, there is also a standard deviation. That is a certain radius where you find 90%, 60%, 40% the probability to be inside the radius. So it's important to understand what is the standard deviation, or the square root of the variance. So we have also to compute this, okay, or the standard deviation in the square root. This is not complicated because it's just put to this. The square modulus is 1 plus the other complex conjugate. Is this summation, well, n, let's say e equals 0 n minus 1, e equals 0 n minus 1, e, and then you multiply by summation of j equals 0 n minus 1 x of j pj. Well, j is not a good variable because otherwise let us put p, so we not mix the complex. So you have to compute this expectation. Here again, the expectation of the summation is the summation of the expectation, and so you have the double summation over index e and p, okay, over n term of x of j phi e minus phi p. Okay? So when you do this exponential and this summation for all the possible combination of phi and p, there are all the cases in which e is different from p. If e is different from p, here you have a number that is distributed between minus 2 pi or 2 pi, because it's the difference between two numbers that is minus pi and pi. So when e different from p, you get a 0. Okay? The expectation, the sum of all these terms is 0. But when e equals to p, this number goes to 1. Okay? And if you sum all the number get to 1, you have a big number. How much is this number? So how many combinations are with the same index, e equals to p, over this? How many? You have n, okay? E equals to p, E1, P1, okay? So it means that how many combinations are in this summation? In total?
N squared.
N squared, okay? But of this n squared, mostly are 0 because when these phases are different, so you have different phases spread everywhere. Only when e equals to p, you have a good result. And how many there are of e equals to p? N. E equals to 1, e equals to 1, equals to 2. So there are only n terms that goes to 1. So this means that while this is 0, the variance is n, or the standard deviation is the square root of n. Let's say the power is n, okay? But this happens because you have this random walk. So you are confined at a number that is n if the step is unitary. Otherwise, let us say the standard deviation is square root multiplied by the standard deviation of the step. So you are at the average step of the drunk man. Is a drunk man makes 100 foot, okay? So 100 steps. And you change direction at every, let us say, 10 meter. 10 meter is 1 step, okay? You find a good probability to find the drunk man at which distance? 10 meter multiplied by the square root of 10. So you will find it only in 100 meters. You best search it in 100 meters, okay? But if it is not a drunk man, at which distance you find him? So it makes 100 steps and 10 meters per step. In which circle you find him? 1,000, of course, because he always goes in the same direction and the correct one. So if it is not drunk, it gets 1,000 meters. Because now you combine all the steps coherently with the same phase. If the phase is random, it goes with this. So it means that here you go to the square root of n, and here it's the proportional one. Or the energy here goes to n, and here is n squared. Okay? It seems not a big difference, 10 with respect to 1,000, but if you consider that a black body can have a million of a meter, when you go to the square of a million, you have 1 million of million, that is much bigger than 1 million. Okay? So the square, with respect to the linear, okay, this is a linear and this is a square, that is a parabola. When the numbers are small, it does not change too much. The square of 2 is 4, and between 2 and 4 there is only a factor of 2, and for 1 the square of 1 is 1. Okay? But when you go far and far, the square diverges with respect to the linear. So this means that you get advantage of coherent sources when you have so many, not when you have 1 or 2. Okay? To get 1 of 2, you don't get a significant advantage. And the advantage is the square, and we also learn that we need a phase synchronization. Okay? Well, how you can do this? So now, how you can generate a coherent sources? We generate with this trick, with the guy of the pool. So you understand the principle? Coherent means same frequency and synchronization of phase. I give you the clock, and in the clock you should stamp down, not stamp up. Otherwise, you are counter phase. Okay? Well, if you understand this, let's try to put it in an electromagnetic way. I need many sources, and I need to synchronize them. These are also written in the book, but you find it dispersed, so you must look at it in the good position. So, first of all, I can place the sources in this position. These are elementary sources. Each one generates, yes, question.
You are talking about arrays, right?
Yes.
But if you use the same phase difference between each element,
Yes.
isn't it just pointing towards
Okay, let's look. Yes, that's correct.
It's coherent?
It's coherent. It's coherent.
So why we say it's not coherent in the case?
Well, I don't say it's not coherent. I say, first of all, if the phrase is the same, if the frequency is different, it's not coherent. Do you agree? Okay. You must have the same frequency. Okay. Now the point, of course, someone of you has already a knowledge of array, but this is exactly a lesson also based on array. The point is that array is that I must synchronize all these sources in order that I want to emit a large signal in a particular direction. Because if I say all these guys put let us say, the foot exactly the same time, then they will generate a signal that goes in this way. Okay? And if the signal goes in this way, all the signals sum up together and make a long wave that goes in this direction. Okay? But they are coherent. Do you agree? Then, if I say, no, I want to put a collimated beam pointing in this direction, is a little more complicated, because if you point in this direction, I must create a beam that is different, and the beam should be like this. So this signal, they should, let us say, this, and this one, you know. They should have, let us say, the same circular, so this is a circular of this, and this is the center of this, and this is the center of this. So I can say that I start with this guy emitting a wave, then at some particular time after I say this guy emit a wave, okay? No, so the contrary. So the first is this one. The first taps the water, then this wave propagates and arrive at this point. Okay? After some time, this taps the water. After some time, this taps the water. So they should be exactly synchronized, but they should move in a source that this moves first, and then this, and then this, and then this, and then this. Okay? You understand? So they are synchronized. Okay? But with a different, the phase should be properly tuned according to the direction that you want to go. So, what is a trick? Okay, let us write sinusoid that is more simple. This may be the center, and this is the direction in which I want to have a big signal. Okay, I can start with a sinusoid. Okay, and the signal here arrives from the phase in particular. Then look at the signal here. If I want a big signal here, it should arrive with the same phase. So it means that the sinusoid should be that when I'm at this distance, this phase should be the same as this. Okay? So I should tell this guy to start with a proper phase that depends on this. If I do not tell, this doesn't work. Okay? So if the signal is the generated signal that is transmitted is, let us say, let us make it with a cosinus. 2 pi f0 t. Okay? So how the signal propagated in the space and, for example, arrive at this point at the distance r. Okay? The signal resides at p. It's just this. Okay. You just put a delay. The delay is the distance divided by time. You know that by putting this, you just put this delay. Okay? But this is just for the signal. And of course, you can write it in another way. Okay, you can write it in another way. Agree? Okay, not difficult. But if you look here, okay, this is a constant term. It's a constant phase because this does not depend on the time. Okay, it's a number. And what is this number? The phase. I write here 2 pi f0 divided by c multiplied by r. But f0 divided by c, you remember that is 1 over lambda. So it's 2 pi r divided by lambda. It's easy to remember this. Because it says, if I have a signal that starts from here, okay, and goes to here, okay, and I want to understand the phase. The phase, every time you make a cycle, how many radians you make? 2 pi, okay? The phase is 2 pi multiplied by the number of cycles. How many cycles are there? Is the total distance, r, divided by the length of the cycles, lambda, okay? So, this is the number of cycles. Fractional number of cycles, okay? Actually, the integer number does not account. It's relevant to the final. And this is the radians per cycle. Okay? So 2 pi r divided by lambda. Simple. Okay? If you remember this, you will never forget the relationship. By the way, this is actually, if you put this and you divide by r, this is a spherical wavefront. Because it's a wavefront that has the same phase everywhere at a certain distance. So this, in this position, in this position, in this position, you get the same phase. So the wavefront is this. Okay? But now, in my, let us say, exercise, I approximate the spherical wavefront with a plane one. So this is a spherical, but I do a planar approximation, a plane wave approximation. Okay. How this plane wave, it's much simpler to understand and how this works. So, I say, this guy moves here and arrives with this phase. This guy is in a different position. If I want all the energy to go here, I must say that when this phase arrives here, it's the same as this phase arrives here. But since this guy has a distance that is different, I must compensate with this. So this must start exactly with this phase, because it's the same difference. I will show you again. I will make now coordinate and I will make again this drawing so that we can do the analysis once more in a more efficient mathematical formulation. So let's start that this is what is called ULA. So some of you already know what is an array. ULA, this means uniformly spaced linear array. Last year, 1 year ago, my first homework was about a circular array, for example. There is an homework that I can, but today, every time I change the homework. Okay. So, what means? It means that you have many sources from minus n, for example, to plus n on the x-axis, and they are faced uniformly by the question.
Excuse me, I didn't understand the wave plane approximation.
The
Wave plane approximation.
The wave plane, don't worry, I will tell you again. Okay. I'm interested in this position, okay, P. Well, consider that the array is very small and the position is very far. Okay, so it's here, it's not a good approximation. This is very compact with respect to P. But in any case, what I can say is that P is a position that is defined by an angle. Okay? So the signal that comes here after R, so after a phase that is R divided by lambda multiplied by 2 pi, it's simple, no? R distance, lambda is a cycle, number of cycles per 2 pi, arrive here. But if I want to have the coherent, this signal should arrive here with the same phase. Okay? So I can say how much phase it should have more than this. Okay? Well, I should compensate this excess of path, because this starts with this and has to do this path. Okay? And this starts after, because we have a shortest path. You have also this, yes.
Are we assuming that all the paths are parallel? Since
no, in this point, no. Okay, but usually yes. Okay. I mean, if all the paths are not parallel, the excess of paths actually, well, this is delta x. I don't put anymore. This is R. I don't put anymore. The difference of the distance between here and here with respect to P is just a circle that is centered over P. Okay? So the difference of path exactly is this. This is exactly this minus this, okay? Because it's a circle, okay? But for, let us say, compact array long distance, I can approximate this with a tangent. So here I don't assume that are parallel. When I use a tangent, of course, I assume that the waveform is straight instead of being bended. So here, instead of considering a waveform that is circular, I consider the waveform that is plane. So you understand here. I approximate a plane wave with a circular wave. Okay? Here it's approximation. And then here is the excess of path. Okay? So all the trick is the delta phi that I have to, or let us say, the phi that I have to put with respect of a generic position x. Okay? Because if this is x, okay, the delta phi is the excess of phase that I have to put to go in this direction is exactly this distance, and this distance is approximately x multiplied by, well, if this is a triangle that is rectangle here, okay, this is x by sinus of c. Remember that c is this angle, okay? So c here is again this angle. Is I show you again how it works. So I want to just to put only the certain position. This is angle c, okay? Of course, c is also this angle, and when I make the orthogonal, these two angles, this and this, are complementary to the same angle. This is complementary to this, and this is complementary to this. Okay? So these two angles are identical. Okay? So this is C, and this is also C. Okay? You understand? So if this is X, okay, this is X multiplied sinus of C. Okay? So delta phi is X multiplied sinus of C. Okay. Actually, we must take care also on the sign. Okay, it means that if X is positive, C is a positive, this is a negative, so you get into a positive Y. But remember that this is not a phase. This is just this distance, okay? The excess distance. Okay? To convert it to a phase, you must put the chest distance divided by the distance divided by the wavelength. Remember that you must tell how many cycles you have to increase. The distance divided by the wavelength and multiplied by 2 pi. Okay? So if you wanted to generate a signal, okay, that is directed over a certain direction of C, it's like generating a plane wave. Okay? A plane wave that propagates in this direction. It's the same as considering a plane wave starting from P and going down, or a plane wave starting from the position and going down. It's a plane because it means that when the wavefront is far, I can approximate the circular wave here with the tangent plane wave. Okay? It's very, very similar if the curvature of the plane, if the curvature is not big. Okay? So the curvature is not big because P is far from the center. So I approximate this. In practice, what I do is I have to compute in general the wave field.
Excuse me.
Yes.
The definition of C is not clear. You mean the angle of...
C is not clear.
Yeah. Can you
Again,
clear?
If it is not clear, I will show you again, so until you are not clear. Direction in which you want to see.
Yes.
Okay. Is this clear?
Yes.
Okay. Is this clear? Okay. Orthogonal to the wave. Okay. Pay attention that this is orthogonal to this, so this is again. Okay. See? Is this clear? Okay. So consider this triangle. It's orthogonal here. Okay. So this angle is complementary to this. Okay. So where you find the psi? This. Say psi is psi again. I lost the angle. Psi is this one. This is psi. Okay. And this is psi as well.
Here as well.
Okay. This is complementary to this. Okay. And this is complementary to this. Okay. Now, if this is psi and this is x, okay, this is excessive path, x times of psi divided by lambda. Okay? Then, let us compute the signal that comes at a certain point that is also at a certain point p, that is a certain distance r with respect to the center, and it is emitted by many of this element. Okay? Let us say that I have many points from minus n to plus n. Okay? Well, the signal will be a superposition of all the signal emitted by this. So each one, each elementary element generates a signal. Okay, so each one generates its own signal. But if I want to say I want to propagate in this direction, I must put a proper phase in order to compensate this distance. Okay, so if this distance increase of psi, I must so this with respect to this has a psi more delay, and this has a psi more delay with respect to this is 2 psi with respect to this. So if I want to compensate the psi phase, I have to put a contrary, a back compensation of the phase. So I have to multiply it by minus j multiplied by psi x, psi n x. Okay? So that, well, we can do that analysis. So that this signal has make this function psi to get from this position to this position, but I compensate this phase so that I cancel this phase, so that they will arrive exactly with the same phase. Okay? And of course, this one is the one that has the longest path, and as x increase, I must add more phase compensation to this term. Okay? So this is the signal that transmit every wave, every single elementary element, multiply minus j. Well, this is 2 pi sim c divided by lambda, and then multiplied by x. I can write 2 pi x sim p divided by lambda. But this is just a linear phase term with distance. Okay? So with the position, at the position 0, I don't have any compensation. Here I do some compensation. Here I increase the linear with the compensation. So the phase compensation is linear with the position. And this is a frequency. It's a space frequency, fx. Okay? So, let us, for example, put the model of this signal. The signal if not properly compensated, this signal is an exponential term. It has an amplitude. It's negative, I must put it positive or as the opposite. Because now the phase is negative, okay? The signal is this one, okay? So if I do not put any compensation, okay, this was what he asked me about the compensation. If I don't put any compensation, this is a signal that derives from the different antenna with different distance, and so if they are different distance, I must compensate it. It arrives with different phase. But I can compensate it by putting this term. So this term should be exactly to cancel this. Okay? Because if I plug in this model here, I got R depends by x, of course. It's the R function of x. And then I put this. Okay? So this is a signal that arrives everywhere in the space. So I can generate it as a signal everywhere in the space. If I want to compute this signal here, okay, this is a superposition actually of spherical wave. I just have this is constant for everyone, and then I must add this is phase rotated by proportional to this distance. This is phase rotated with proportional by this distance. This is a phase rotated with proportional by this distance. Okay. So when I sum all the signal here, I have almost nothing. Okay? Why I have almost nothing? Because this distance changes, and then I have a summation. If I consider only this term, I have the summation with random phases. So, okay? You understand? So, if I generate a coherent signal here, but I look in this position in the space, I have random phase, because this distance are different. And as the distance are different, the phase change. Okay? You agree? So, I get almost nothing by emitting and looking in this direction. Okay? I get a small signal because they are not coherent. But if I want them to be coherent, I must then put a compensation for each signal. So before transmitting this signal, so this single signal is compensated by a proper phase. The second signal, that has a different distance, is compensated by proper phase. It means that in the end, these two terms compensate together. So I must tune the phase according to every single position of the antenna in order to compensate exactly the distance. You understand the trick? Okay.
I didn't understood
The compensation.
Why is it
Because I want to have a big signal in a certain direction.
okay. No,
Okay.
the last mathematical.
The last mathematical is just to tune this value to be exactly this value. When you just have to make C of x is 2 pi f0 R of x divided by C, but we see that this is exactly this number. 2 pi f0 divided by C, 2 pi r divided by lambda, yes, 2 pi f0 divided by C is 2 pi r divided by lambda. And then here you have to make varying with red. So it is a phase. So this number is like writing 2 pi fx of x. Okay, you understand? So if I make the proper compensation that depend on fx, and fx depend on the direction. So for each direction, I should use a different compensation. Of course. For example, and well, when I make this compensation, then this cancels with this signal is taken out of the summation, and this is taken out of the summation, and the summation make a gain that is 2n plus 1. Okay? So you have the coherent summation of all the signal. Okay, that's easy. So that's how it works. Let us make a simple case. This is a general case, but I want to make a much more simple case. Let you assume that you want to generate a signal that coherently propagate only in this direction. Okay? Then it's clear that if you are very far, all the distances are all the same. This does not change too much. So the distance tends to be identical if this is very far from this. So if I wanted to propagate in this direction, I use, remember that the frequency, the phi, is 2 pi fx multiply x. Okay? But fx is sinus of c divided by lambda. Okay? If I want to go into this direction, what is c? Remember that in this direction, c is this angle. Okay? So if you are in this direction, the angle is 0. So this means that fx is 0. If fx is 0, the phase is the same. So I do not any phase compensation because x, the j0 is 1. So I just say all the guy tap together. And if they tap together, they generate a wavefront that is made in this position. A plane wavefront, okay? That has a maximum in this direction, okay? To understand that, because here it's a direction that is more or less at the same distance. Here again, consider that this is not the correct scale. The correct scale may be that you are in this position and you have a few antennae here, and you see this point is more or less at the same distance from all this one. There is actually a variation of the distance that is due to the spherical wavefront, but this phase is a very small number, or the number combined with the same phase. Okay? So I don't compensate the spherical effect in a first order. If the array becomes very big, I should also compensate the spherical effect. And the radar will compensate. But for many cases in which, in optical, for example, your lens may be 1 millimeter, and you're looking at 10 meters, it's nothing. So you can just do this. But if the signal goes in this direction, then we must understand how many energy, for example, goes in another direction. So how much energy I found at a psi different from 0. So this is a very simple case, because I can just compute the signal that is a function of t, and in any angle of c, I just do the summation. So I just sum between minus n and plus n the signal generated by all these antennas. Each single antenna generates x, j, 2 pi, f0, t, and then I must delay for this distance. Okay? In a generic position c, okay, the distance is t0 minus r0 divided by c. This is R0, this is R0, and then I must add this additional distance, okay? This term. This term is exactly equal to this term, okay? That is the same term that is sinus of c multiply x divided by lambda. I sum all the signal. I say everybody tap with the same phase, okay? So I don't give a particular phase. I say tap exactly synchronized. If they are synchronized, the waveform goes in this direction. You understand this? It's like you put all together waveforms that becomes big and big simultaneously. So the waveform moves in this direction. Okay? You understand this? If you wanted to bend the direction, you must give a different phase. You must start with this, then wait and then start the second, and then start the third, okay? And then the waveform goes in this direction. So you understand it, how it works. I just give the starting point of each waveform with a sufficient delay so that when this front is arrived in this position, this front in this position, this front in this position, and this front in this position, and then I bend the front. And if I give the proper delay, I can put any bending on the front. Okay? You understand that? Simple. Now I say all the guy tap with the same, start with the same time. If they are perfectly synchronous, the energy goes in this direction. But I want to compute how much energy goes in a different direction from 0. I know that in 0 I will have the peak, but I want to understand how much I get in other direction, because I want my beam to be very small, okay? And then this is what I can get, because this is okay. Then the sum. Well, I also put J phi0, where phi0 is 2 pi f0 minus 2 pi f0 r divided by c, and just put x of J 2 pi fx, well, fx is minus sinus of c divided by lambda. This, okay. So this is a signal that every one of this guy is transmitting, okay? So the total signal I get in this direction is the signal that everyone is transmitting. This is good. So if they are, instead of putting a sinusoid, they are putting another signal, a music, here again I get the same music, okay? But this is a constant term, and this is also a constant term, but a constant term that depends on this, and so depends on the angle. So this means that this is a sort of gain, a number that can be very small or very large. That depends on the angle, depends on the frequency, and depends on the angle. Actually, this is the Fourier transform of a constant, okay? So is the Fourier transform of a signal that is made in this way, from minus n plus n. Okay? The Fourier transform of a rectangle. Okay? And the Fourier transform of the rectangle have a closed form translation. So I can say that in this condition, GDP is approximately a sinc. Actually, as this is a discrete signal, is a periodical sinc. So this is a sinus of pi great pi 2n plus 1, that is the total number of elements, fx, okay, divided by pi fx, and there is also to write the spacing of the antenna, fx here, or sinus. It's a Fourier transform of this signal. The x is the spacing between the elements. Okay? This is my gain. This is a directivity gain. How is done this? It's just the Fourier transform of this signal. This is let us say signal theory, discrete signal theory. How is done this function? How it works? Let us put, you can put an fx and then you can put a G. Or I wanted to cancel everything because now, sorry, the total signal that I get here is the transmitted signal by HF multiply a constant phase term, multiply a gain that depends on the echo, nothing more. Okay? I take this and I cancel this. Because this now it's very simple and I want to have the whole blackboard to show you how it works again. So this means that the signal that you measured here is a signal that each array is transmitting. Okay? Each one is transmitting. Multiply by a first term. What is the first term? The first term is the number of cycles from the center of the array to this position. So this P0 is clearly R0 divided by lambda multiplied by 2 pi. Okay. This term from the center of the array. And this phase, this gain, is proportional to the summation of different contribution with different phases. So this gain is a resultant of the summation of the different distance. And how is done the gain? The gain has a very simple expression. It seems complicated, but actually, if you put as a function of the frequency, if the frequency is 0, what you get? Approximately, this is a sinus and this is a sinus. If the number is smaller, you can delete the sinus, okay? Because the sinus as the angle is the same. And then when you make this, what you get? Pi and pi simplify, fdx and simplify, fdx simplify. So at frequency 0, you have 2n plus 1. Okay? It means that orthogonal to the array, you have the maximum gain that is the total number of elements. It's simple. They are all equiphase, and the result is a coherent summation of all the elements. Okay? Then, what happens when you increase this function? Okay? This angle is much bigger than this. So this assumes that it's almost constant. This changes only when fx is equal to 1 over the x. But when you move this angle, this is approximately a sinc function. So if this is constant, this you can understand is like a sinus of p 2n plus 1. 2n plus 1 dx. What is 2n plus 1 dx? This is the total length of the array. So you can write it the total length in x of the array. And this is fx. This I approximate when this number, when fx is much smaller or 1 over the x. Okay? So for small frequency, I have this. And this is a sinc function. Okay? So a sinc function is a function that has this first 0. At which frequency is the first 0? The first 0 is when you have 0. When you have this number is pi, and this number is pi when fx is 1 over Lx. Okay? So this is 1 over Lx. And then you have a second 0 that is as 2 over Lx and so on. And then you have a third 0, it's a sinc function. Okay? This, when this number is small. Okay? When this number becomes bigger, the problem is that when fx is equal to 1 over the x, here you have another 0. So you have another 0 divided by 0. So if this is a periodic, if fx increase over the x, you get the same number. So you start increasing, and this is when fx is 1 over the fx. Okay? So it's a periodical gain. Okay? And then you can map that this is a gain as a function of the frequency, but you remember that as a function of the frequency, you can put what is the psi, okay? Because you remember that fx is the sinus of psi divided by lambda, okay? So fx is the sinus of psi, is like so. So this means that this gain is mapped in an angular plane. So you establish a particular angle, you have the frequency, and from the frequency you get the gain. And this you can map in this space. So you can start from an angle. You have this array. If the angle is 0, the gain is 2n plus 1. Okay? If the frequency is 1 over Lx, so which angle correspond? Correspond to this. So sinus of psi divided by lambda is 1 over Lx. If the angle is very small, instead of sinus you put psi. So if psi is lambda over Lx, you have a 0. So there is a direction that corresponds of lambda over Lx, in which the gain is 0. So when you increase the direction, a polar plot of the gain will say that the gain here in this direction is 0. In this direction is so. And then when you increase up to twice this value, then you have a second lobe, you have a smaller gain here, much smaller than 2n plus 1, and then you have another 0. And then you have a gain, and then you have another 0. You have all these cycles. Then cycles become increasing, and you have a second main lobe that is in this direction. Here, the main lobe is as high as the first because when this is 0, you have again a 0 divided by 0. So this again, this number divided by this number. Because this is periodic, when this is 2 pi, 1 pi, 2 pi, and so on, the sinus is always the same number. And then you get, okay. And now the pattern is symmetric. So here is so. Okay? So there are 2 points. First of all, you have this grating lobe. But you can remove this grating lobe. How you can remove this grating lobe? You just want this grating lobe to be much higher than pi, so you don't have this. Okay? Physically, to have this much higher than pi, look at this. This happens when the x is 1 over fx, okay? It's enough to say that it's like a sampling. What is the maximum sampling when you have, because this is just a sampling array. When you have an horizontal frequency fx, and you don't want to have an alias, what should be the sampling step? The x should be lower than, for the sampling theorem, you have a frequency fx, and you don't want to alias. How you must put the sampling step?
2 times the frequency.
Not twice the frequency.
Half.
I mean, if you have a sinusoid of frequency fx, this length is 1 over fx, because it's a period that is inverse. How many samples you should have per period? 2 samples. Okay? So this means that the sampling, at least, let's say, less than 2 samples, more than 2 samples. So the sampling interval should be less than half of this. Okay? 1 over 2 fx means this angle. 1 over 2 sinus of C, you must satisfy this relation. Okay? Well, if sinus of C is 0, it's not a problem because the x can be any number. Okay? Because the sinus of C is 0, this goes to infinite, and then in the x is good. But if you wanted this to be always true, how you should select the x? You should get the minimum number that you get from it, not the maximum. And what is the minimum number that you get from it? Minimum, let us say, of course, in absolute. You get the minimum for which sinus of x?
Lambda alpha.
Lambda alpha. Okay. So if you put x in minus lambda alpha, you're always true. So you have to put the antenna that are spaced of alpha wavelengths, okay, or less than alpha wavelength. And you don't have this cycle, okay? This disappears. So with a proper spacing of the antenna, you avoid the grating lobe. When you avoid the grating lobe, then all the energy is concentrated in an angular portion, as this angular portion is approximately this width. And this width is approximately lambda divided by s. It's written this. Okay? So the V0 is approximately the minus 3 dB. So is Fx, delta Fx is approximately 1 over Lx. But delta Fx means delta psi divided by lambda is approximately 1 over F, and delta psi is approximately lambda divided by F. Okay? Correct? So, the total aperture here is approximately lambda divided by Lx. And this is simple. Okay? This is how you generate a collimated beam. Okay? Let us do a very simple exercise with, for example, a laser. Okay? Remember this. If the antenna is continuous instead than having a ray, you get the same result. So if the antenna is continuous, you get that the pattern, instead of being periodic, it's just a sync. So you don't have the periodic effect for a continuous antenna. But still you have the same sync pattern, I mean the same maximum direction and the same collimated line. So let us see what happens, for example, when you have a laser and you have a collimated beam. Let us put some number. If I want to summarize my direction in just a graph, I put this. If the signal comes from this direction, okay, and you make a cycle in this direction, this cycle is lambda, okay? But horizontally, you design a wavelength whose size is lambda x. And this lambda x, so when you have a plane wave that comes from some direction, you just have a plane, this corresponds to an horizontal plane wave, okay? If the direction is this, the wavelength is this. If the direction rotates, so for example, if you move in this direction, you see that as this is always lambda, okay, and this is lambda x. So when you move the direction in this orthogonal, the horizontal frequency, the horizontal wavelength goes to infinite and the frequency goes to 0. So 0 corresponds to orthogonal. If you move this in this direction, you see that the projection of the array, so if this is illuminated with a varying wavelength, the varying wavelength on the ground, the array, becomes smaller and smaller, and when the signal comes from here, you have the shorter wavelength that you can, that is lambda x is equal to lambda. Usually, lambda x is equal to lambda divided by the sinus of c, okay? So it could be infinite, okay? And we put exactly the opposite with the frequency. Fx is sinus of c divided by c. So it's immediate to understand by just saying that when the signal varies here on the linear array, I see this. This can be a continuous frequency if I have a continuous array, or can be a discrete sinusoid if I have just an array. So I observe this only in some position. But then if it is a discrete sinusoid, you know that I can be ambiguous because I can have a multiple or not, depend on how you make the sampling frequency. So you should tune the sampling just in order to avoid that the maximum frequency that is this is aliased. So 2 samples per cycle. So 2 samples per cycle you don't alias this. And all the other direction provide you a longer wavelength, so you are always sure that it works. So that's just simple. But let us consider a laser, okay? A laser, typical laser, for example, a laser is a monochromatic source. It is exactly as a radar. In fact, a laser has a single color, for example, red. Let us consider that you have 1 meter by 1 meter surface. 1 millimeter, not 1 meter. A square meter, okay? A laser is a diode, it's very, very, very small, okay? And let us consider that you have lambda that is 1 micron. 1 micron is near infrared, okay? So it's infrared, you don't see it. You remember that up to 800 nanometer you see the signal, the wave, so this is a near infrared, the far infrared can be 10 micron, okay? And let us consider that you have, well, we have everything 1 milliwatt. Very small power. So, first of all, compute the temperature of the laser. So which is the temperature that you get as a black body? Okay. The temperature is very easy because you use Boltzmann, Stefan Monza. Power by the laser divided by the surface of the black body, okay, is sigma temperature of the laser. Okay. The power of the laser is 10 minus 3 watts, okay? And the surface of the black body is this, 1 millimeter by 1 millimeter. So it's 10 minus 3, like 10 minus 3. And this divided by sigma, and making the 4 square root gives you the temperature, okay? So if you compute this by using Stefan constant, you get that the temperature of the laser is approximately 364 Kelvin, that corresponds to 90 degrees. Okay? 90 degrees is nothing compared to the sun. Okay? You remember the sun is 5,000 degrees, so it's bigger. So let us compute how much energy you get on the surface from the laser. So consider that you are looking at the laser at a 10 meter distance. Now let us compute how much is this width, okay? Is the width of the laser beam at the 10 meter. Okay? So this approximately the same in the two directions, because also this is 1 millimeter. So delta at 10 meter is linear, is this angle multiplied by the distance. The angle is lambda divided by L, okay, multiplied by L. I use lambda divided by L, that is uniform illumination. And this is, lambda is 1 micron, 10 minus 6. L is 1 millimeter, so 10 minus 3. R is 10, okay? So the angle is, this is 10 minus 3, and this is 10 minus 2. 10 minus 2, so it's 1 centimeter. So the beam at 10 meter, is 1 centimeter. Of course, at 100 meter is 10 centimeter. So the resolution, the width of the beam increases with the space. And this is not the best laser that we can do. We can also use a higher frequency. It has smaller wavelength. You get a better result. Or you can use a bigger emitter. So there are bigger emitters. Okay? Then the point is that how much power you get at this distance. So at this distance, how much watt per square meter you get? Okay? Power of the laser divided by the surface. Okay? Well, you can consider the total power, and what is the total power of the laser? Is 1 milliwatt. Okay? And it is distributed over an area that is approximately this area. Is 1 centimeter by 1 centimeter. Okay? So approximately is 0.1 centimeter. Yes. 0.01, so 10 powers minus 2, 10 powers minus 2. Okay? So as, let us say, power per area, this is not very big, okay? Because it's just 10 watt per square meter. Okay? 10 watt per square meter. And let us compute how is the radiance observed by the laser. Okay, not much better. So the radiance observed. Okay? Well, if you wanted to compute the radius, R, remember, that is the total power of the laser that you can get divided by the area of the receiver, okay, multiplied by delta omega. This I call orthogonal area, okay? Okay, the orthogonal area. Well, we already know the power divided by the orthogonal area. The power by the orthogonal area is 10 watts per meter, this number. Okay? I have only to divide by the angle under which I observe the laser. Remember that this is the angle in which I observe this solid angle. I'm at 10 meter and I observe 1 millimeter by 1 millimeter. So delta omega is the surface, so 10 minus 3, 10 minus 3, divided by the square root of the distance, so 10 plus 2. So this is minus 3, minus 3, minus 6, minus 6, minus 8. 10 minus 8. So I have to put here 10 divided 10 minus 8. And this is 10 plus 9. Okay. So remember that this is a huge radiance. Is much bigger than what I get from the sun. if I wanted to compute what is the temperature that I see from the laser, the equivalent temperature that I observe, remember that this is computed by this radians 10 minus 9. Okay. Then you should multiply by pi divided by sigma and put the 4 square root of this. 4 square root. And then you get 708,000 Kelvin. Okay. So if you look in the laser, you see a temperature that is much higher than the real source temperature. So the source temperature is 100 watt, 100 degree. Okay. Here you see 7,000 degree. Okay. That's why it's very dangerous to look in the laser, because the temperature is very high. Why this is different from the sun? So I mean, if the sun is 5,000, if I look at the sun, I look 5,000. Okay. Why you can tell that the temperature is different? So here I have 100 degree, but if I look to the laser, I see like a source that is 7,800 degree, okay? Because the laser is not a black body, okay? So we got exactly at the point in which we begin. I mean, if a laser is a black body, it would be radiating in all the space isotropic, okay? And so it means that its whole power will be distributed over a total angle that is 4 pi. That is the total angle, okay? But what is really the total angle in which the laser confines energy is this, okay? So the delta omega of the laser is 10 minus 8, okay? It means that you have a huge gain in angle, okay? So it means that all the energy of the black body of the sun is uniformly distributed in an entire sphere of angle. But instead the laser has a small energy, but all this energy goes in this angle. It means that if you look from here, 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 or here, you don't see anything. So for most of the direction, you see a source that is 0 degree. It's not emitting anything, because you don't see any light, okay? But if you see exactly in this position, you see an enormous light, because all the power is concentrated only in one direction. That is why even if the laser is 1 watt, or let us say 100 of Celsius, instead than 5,000 as the sun, its equivalent temperature is higher, because all the energy, the gain in omega is a spectrum. So the laser concentrates only in one 10 minus 8 portion of the space, but this means that in that space you see all the power, and it is like the whole power, it's amplified by a factor of 10 8. And it's amplified by a 10 by 8. Since the power goes like the temperature goes by the square root, then you have an amplification that is the 4 root of 10 minus 8. So you have 100 amplification in temperature. Okay, 100 starting from 90 is approximately 9,000. So you gain. You see a lot of temperature, because only if you look in one direction, you see all the power going to you. It's much worse than if you have a smooth body that is distributing all the temperature and look in one direction. You know. We started telling you what is the advantage of a coherent waveform, and this is the advantage of coherent waveform. A lot of power only in one direction, and a very small point here, only 1 centimeter by 1 centimeter at 10 meters. Okay, you can do it better. Okay.